Okay, so in the last lesson, we saw how scalar multiplication and matrix addition are pretty straightforward. They kind of work the way you might think. Matrix multiplication, not so much. It's not a matter of just taking the corresponding elements of the two matrices and multiplying by each other. We could do it that way, but that turns out not to be very useful. And what does turn out to be useful is a somewhat more complicated definition that I'm just going to show you now. Okay, so in general, if we have matrix A multiplied by matrix B, I'm going to write it out in terms of the elements. So let's make this A11, A12, A21, A22. That's my A matrix. And my B matrix, we're going to have, I think, 3 columns in this one. B11, B12, B13, and 2 rows. B21, B22, B23. What does that equal? Okay, here's what we're going to do. I give myself space to do it. We're going to take, to get the first row, first column of that product matrix, we're going to take the first row of the lead matrix and the first column of the lag matrix, and we're going to multiply corresponding elements and add them up. Okay, that's just a lot, so let's just do it. Okay, so take the elements of the first row of the lead, first column of the lag, and multiply corresponding elements and add them up. So it's going to be A11 times B11 plus A12 times B21. Okay, so I've got my elements of the row of the lead and the column of the lag, and I've multiplied them and added them up, and that's the first element of the product. Okay, I told you it was going to be weird, and it is. So now to get the first row, second column, I'm still going to have of the product, first row, second column of the product, I'm still going to have the first row of the lead, but now I'm going to take the second column of the lag. So that's going to give me the first row, second column here of my product matrix. Okay, so that's going to be A11, B12 plus A12, B22. Okay, so again, it's sorry, I just pointed to the wrong place here. It's the elements of the first row of the lead again, but now the second column of the lag, and it's because that is the second column in the product matrix. Let's just keep going. It's easier once you do it a few times. For the 1, 3 element of the product, still the first row of the lead, but now the third column of the lag. So that's A11 times B13 plus A12 times B23. Okay, so that is all I've got in my product matrix here. Deep breath. Okay, so now to get the second row of the product, we want the 2, 1 element of the product here. Oops, didn't want to write that. I just wanted to kind of designate the place. So to get the element that goes here, this is the second row, first column. I'm still going to take the second row of the lead, first column of the lag. Okay. So I have a 2, 1, B11 plus A22, B21. That's my 2, 1. I'm sorry, it is 2, 1. Yes, 2, 1. Second row, first column of the product matrix. And to get the second row, second column, I'm going to take the second row of the lead and the second column of the lag. So that's A21, B12 plus A22 times B22. And for the second row, third column of the product, I'm going to take the second row of the lead. I've been doing that all along, now times the third column of the lag. So it's A21, B13 plus A22, B23. And that's it. Okay, that was kind of a lot. I'll erase to make my to make up a little more space here. This is my product. Okay. So the ijth element is the elements of the ijth element of the product is the ith row of the lead times the jth column of the lag. And if we want to write that out in a sort of more compact form, we can say that C, matrix C, is the product of A and B, matrix multiplication product. That tells us that this ijth element of C is summing, this K goes from 1 to N over the rows of the lead, okay, AIK times BKJ. Okay, so let's just kind of look at this sum here. What we're keeping constant within the sum is the column of the lead, okay, because that has to match the element in the product that we're looking at. And we're keeping constant here, I'm sorry, is the row of the lead and the column of the lag. And those are the things that have to match the product. And then we're taking the elements of the row. Okay, so those are the different columns, are the elements of the row, and the elements of the column are the rows here, and we're adding them up. Okay, most people find this kind of counterintuitive, hard to remember. As we go through this lesson, especially the next, I'll show you some examples that I think will help you remember why it works this way. But let's just go to an example. In the context of the example, we'll talk about conformability, but I also think it's kind of easier to see what's going on once we have numbers. Most people remember matrix multiplication in kind of a visual. I'm going to take the elements of the row times the elements of the column and multiply them together. So let's just look at a little example here. So we're going to have A times B. Let's set my A matrix B 3, 5, 0, 2, 1, 2, and my B. Oh, let's just even make it a column vector to keep things nice and simple here. Okay, something that you always want to do before you try to multiply matrices or before you're thinking about multiplying them is think about whether they're conformable and what do we need for them to be conformable. What we need is for the number of rows, I'm get ahead of my writing here, conformability. Shall say it in the other order seems a little bit more reasonable to me. The number of columns in the lead matrix must equal the number of rows in the lag matrix. Okay. And what people do, what you should get in the habit of doing when we're doing matrix equations, really, really good to get in the habit of just writing those dimensions below matrices, okay? So the dimensions of A is a 3. No, it's not. I'm kind of switching my rows and columns a lot here. And actually, let me say something about that. There's two mistakes that are really easy to make over and over again with matrix multiplication. I do it a lot. I don't think it's just me. One is the sort of the switching the rows and columns, both as you're talking about it, but it's also kind of easy when you're picking things to switch the 2, 1 and the 1, 2 element. The differences seem so minimal, and just heads up for that. The other thing, maybe I'll say it, I'll probably give you an example, sad to say, of this mistaken action is the process of doing, say, matrix multiplication is not hard. We're just, kind of adding and multiplying numbers. So really just kind of basic arithmetic, but you can kind of get on autopilot because it's not hard. It doesn't keep you engaged in that way. And you can start doing things in the wrong pattern. So you in your life are not going to be doing a lot of matrix multiplication because of those two things that I just mentioned. The practice of matrix multiplication is something that human beings tend to mess up a lot. Computers are really, really good at. So most of the matrix multiplication that you need done for you, computers will be doing. But you do need to understand it well enough to know what those numbers that the computer is giving you mean. And so while you're doing this computational stuff, best advice I can give you is just go slow, take a deep breath, check yourself a lot. So with that, getting back to where I made the mistake, what we're doing here in writing the dimensions of A, we're writing the number of rows first times the number of columns. That's how we always do it. So it's 3 times 2. I did it again. One more time and I'll start the video over, but let's just try writing it 2 by 3. Okay. Maybe you guys could learn from watching me do it wrong several times. The right way to do it, I'm happy with the way I'm doing it now, is 2 rows by 3 columns. I think I kind of messed myself up by having the numbers 3 and 2 where I do here, but life will throw stuff like that at you. Dimension of A is thus 2 rows by 3 columns. Row 1, row 2, 3 columns. And let's go back to writing here. There's a 5. And B is 3 rows by 1 column. Okay, so yes, now we've correctly written the dimensions of each of these matrices underneath them. And the point of doing that, here's the cool thing. Okay, when you write the dimensions, you get 2 things for matrix multiplication. First of all, the inner numbers. What are the inner numbers? The inner numbers indeed are the number of columns in the lead, that's this, and the number of rows in the lag. These must be equal. They must be equal for conformability. If you write the dimensions correctly of the lead and the lag, and those inner 2 numbers, columns in the lead, rows in the lag, are not the same, you can't do the multiplication, so you got to figure something else out. But the other thing you get that is also cool is, what do you get from the outer numbers? The outer numbers are the dimension of the product. Okay, so that's kind of useful. So what we're saying here is, yes, as we've got them written right now, AB is conformable, and the dimension of the product will be 2 by 1. Okay, it will be these 2 outer numbers. So let's just go to a new page and do that. So same thing, 350, 212 times 150. Let's see if I can redeem myself and write the dimensions correctly this time. The lead matrix has 2 rows times 3 columns, and the lag has 3 rows times 1 column. And we do check that these are conformable. And here we can say product is 2 by 1. The product will have the number of rows that are in the lead and the number of columns that are in the lag. So, okay, So we're expecting a 2 by 1 matrix, and to get that first element, the 2, 1 element, I'm going to take the first row of the lead and the first and last column of the lag. So I get 3 times 1 plus 5 times 5, that sounds like 28. And to get the, that's an 8, 2, 1 element, I take the second row of the lead, and again, that first and only column of the lag. 2 times 1 is 2, 1 times 5 is 5, it gives me 7, and 2 times 0 leaves me with 7. That is indeed the answer. Okay, that's not too bad. Notice, however, so this is fine. But remember, this was our A and this was our B. If we look at B times A now, so we put B in front, 150 times 350, 212. Let's do our same thing. The B is still 3 by 1, and A is still 2 by 3. Okay, but now these are not the same. So even though AB was fine, we could do that product, we can't switch the order. The A not conformable. Another way to say this is B pre-multiplied by A is fine, like we said, but B post multiplied by A is not conformable. Not conformable. Okay, so let's just kind of think about that. One thing that's showing us is that matrix multiplication is not commutative. In fact, it's so not commutative that you might be able to do it with one order and not do it with the other. You might be able to pre-multiply B by A, but not post-multiply B by A. And we have to always be vigilant about that when we're working with matrices, that we're so used when we're thinking about multiplying real numbers together to think that 3 times 4 is the same as 4 times 3. We just do that so automatically, and we have to unlearn that a little bit with matrices and stop ourselves from thinking that A times B is the same thing as B times A. Sometimes one can be defined and the other one not. Even if both exist, they're not necessarily equal. Okay, so let's look at an example of that. Even if BA and AB both exist, in general, they're not equal. AB is not equal BA. Okay, so let's keep that same A and let's add a column to the B matrix, and you'll see that's going to improve our ability to do the multiplication, at least in both ways. Okay, so we have A continuing to be what it was before, and B, what was it, 150. Let's add another column on here. Okay. And just like always, I'm doing my dimensions here. A is 2 by 3, B is 3 by 2. This is good. This checks. They are conformable. And the product in this case will be 2 by 2. And let's write that out just to going. So I'm kind of expecting a 2 by 2 here. Doing the multiplication, the first element, just like it was before, is 28. 3 times 1 plus 5 times 5, 28. To get the 1, 2 element, the first row, second column, I'm going to take this 350, multiply it by -102. So I will get -3 plus 0 plus 0, sounds like -3. To get the 2, 1 element, the second row, first column here, I take the second row of the lead, the first column of the lag. So that's 2 times 1 plus 5 times 1 plus 2 times 0 is 7. Last element is the second row of the lead, second column of the lag, -2 plus 0 plus 4, sounds like 2. And that is my, my product matrix here. All right. So yeah, I think I can, trying to decide if I want to go to another page. I think I can do BA on the same page. It's kind of helpful if you can see them both together. Okay, so reminding ourselves, this is A, B, this is B multiplied by A. Of course, you could say it the other way. You can also say this is A post multiplied by B. So you could say that one of two ways, but it's not the same thing as B post multiplied by A, and that's what we want to convince ourselves of right now. So now for BA, we're going to start with 150, -102. There's my B, just like it was before. Post multiplied by 350, 212. Checking our conformability. B is 3 by 2, just like it was before. A is still 2 by 3. These numbers match. That's good. The outer numbers say that the product is 3 by 3. All right. So we're expecting now to get a bigger matrix for this product, for B post multiplied by A, or if you want to say it the other way, A pre multiplied by B. Okay. And so same process. I'm going to go through to get the 1, 1 element of the product. We take the first row of the lead, first column of the lag there. And so that's 1 times 3, 2, there's a 1 there. 1 times 5 is 5, minus 1 is 4. 1 times 0 is 0, -2. So I've just taken this. Let's see, I do not want to have that in there. So here on the highlighter, yes, taking this row, multiplying it by this column to get 1, by that column to get 4, and by this column to get -2. Now for the second row of the product, we're going to take the second row, 50 row of B, and multiply by each column of A to get the 3 elements in the second row there. So the 50 row multiplied by the 3, 2 column gives me 15, 25, and 0. Okay, then let's just check that. 5 times 3 plus 0 times 2, so it's like 15. 5 times 5 plus 0 times 1, that's good. 5 times 0 plus 2 times 0, all good. And for the third row of the product matrix, we're taking this third row, multiplying it by each column to get the 3 elements of the third row of the product. So that will be 0 times 3 plus 2 times 2 is 4, 0 times 5 plus 2 times 1 is 2, and 4, and there indeed is B post multiplied by A. Okay. So, okay. Some comments here. From the first example we did, we saw that matrix multiplication won't even necessarily be defined in both orders. So it's possible to be able to pre-multiply one matrix by another, but not post-multiply it. And we always have to be thinking about that. It's not like it's some kind of unusual exception that hardly ever arises. It's very common if you just pick two arbitrary matrices to not be able to multiply them. Second of all, even when the multiplication is defined in both directions, so both pre-multiplication and post-multiplication by the same matrix are conformable, you won't necessarily get the same answer. You won't necessarily get something of the same dimension. If you do get something of the same dimension, you won't necessarily get the same numbers. Okay, so we really have to be much more self-conscious about matrix multiplication than matrix addition. Matrix addition, kind of what we're used to with adding up numbers, serves us pretty well. Very different with multiplication. Okay. One fact that I'm just going to put in here, I'm not going to make too much of it, but sort of an interesting way that transpose interacts with matrix multiplication. If we have the product AB transpose, that is equal to B transpose times A transpose. Okay. So, like I said, I'm not going to belabor it. It's true. You can come up with a little example and convince yourself that that it works. I think if you do the example, you'll sort of see how the example generalizes. So again, let me sort of emphasize the three take-home points here. About matrix multiplication. Conformability often fails. So don't just see two matrices, don't assume, oh, I can multiply them. I would say assume you can't and convince yourself that the dimensions are such that you can do the multiplication. It's not commutative. BA does not necessarily equal AB. Some special cases where it does, but it's generally not something that you should assume. And that when you do matrix multiplication, dimensions change. Okay, in the example that we just finished, we had 2 by 3 and a 3 by 2, and when we multiplied them, we got completely different things. We got either a 2 by 2 or a 3 by 3. Okay, so dimensions change multiplication. All right, so the next lesson is going to walk you through two important applications of matrix multiplication, which I think will help you sort of understand why it's defined in this kind of complicated way and why we care about it. I personally find that those examples help me remember the process. So I'll see you then.